In the current lecture, we are continuing the topic solid state. In the current lecture, I'd like to discuss here what is the difference between crystalline and amorphous solids. Firstly, we know there are the different properties of the solids. Interparticle distance is least, interparticle force of attraction is the highest one. They shows the least diffusibility. Generally, solid state of matter having the high density. Solids are having fixed shape, fixed volume. Okay, they didn't fill container completely. And one more important thing, constituents of solids oscillate to its mean position. Say for example, this is the board. We are thinking it's a stationary one, but what the science says, the constituents of the board, they are oscillating to its mean position. Say for example, here there is a one constituent, so it is oscillating to its mean position. Okay, like a pendulum of the clock. Now let me continue after the physical properties of the solids. Next part for the current lecture, that is solids are of the two types broadly. Okay, crystalline solids and amorphous solids. So the points of differentiation I'd like to discuss here. Here I'll give you the hint first of all. The hint is A C H M T O R E. So with the help of these abbreviations, I am going to explain some points of the differentiation. So let's begin. Here at the left side, I'll write about the corresponding property of crystalline solid. Okay, and here I'll write the corresponding property of the amorphous solid. Crystalline solids are also known as non-amorphous. Amorphous solids are also called as the non-crystalline. Okay, so the first point of differentiation, A, means just abbreviation I give for recalling for the examination point of view. What about the crystalline solids? Anisotropic. Crystalline solids are anisotropic in nature, while amorphous solids, they are the isotropic in nature. See, in case of the crystal, I'll tell you what is the meaning of anisotropy and isotropy. Here, for example, crystalline solid, one outline I am trying to draw. The constituents are arranged in a regular systematic three-dimensional pattern. Regular systematic three-dimensional arrangement of the constituent, it is there in case of the crystalline solid. Okay, it might not be always hexagonal, it may be of the different shapes, but the shape should be that repeating pattern is to be get repeated again and again. Here you are seeing the repeating pattern is get repeated. So at the corner, okay, here there are the constituents. I hope you understood. Here there are the constituents of the crystalline solids. Now what about the amorphous solid structure? Amorphous solids, very random arrangement. Say for example, these are the constituents. Okay, the amoeba is get drawn. Okay, but here we have to draw it like this. Irregular arrangement. Okay, the constituents, three-dimensional arrangement of the constituents is irregular, not definite, not fixed one. Now here anisotropy. Anisotropy means what? Ability of the crystalline solid to show the different values for the certain physical properties when measured in a different direction. For example, electrical conductivity, thermal conductivity, dielectric constant, dipole moment. Okay, suppose if we measure a certain refractive index from this direction, so here we have the certain specific type of constituents. We are getting value, say for example X value we are getting. If we measure the same property, refractive index, in this way, suppose if we measure, so here there is no any constituent, so for that refractive index we are getting the value Y. Suppose if we measure in this direction, so next set of combination will get. So when the certain physical property measured in a different direction, we are getting the different value for that property. That is the anisotropy. Here anisotropy with reason I told, that is about the crystalline solids. What about the amorphous solids? They shows the isotropy. Isotropy means what? When the certain physical property is measured even in a different direction, we are getting the same value. For example, here physical property we measure in this direction, we are getting, say for example, value A. If we measure in this direction, we are getting value A. Here if we measure in this direction, we are getting value A. Now the very simple common question one may ask, sir, once you are saying here these are the certain type of constituent, we are getting this one, these are the another set of constituents, so we are getting the another values for the property that we understood. But here also, say for example, here the constituents, bond distance, bond length, that is different. In this direction if we measure constituent, bond length, bond distance is different, here also it is different. So why we are getting the same value? See, we can support it, say for example calculator we have, and the limit of the calculator is of, say for example, 8 digits, okay, and two 8 digits figures if we multiply, the answer should be a very big one beyond 8 digits, correct? So that instrument is unable to analyze, so we'll get answer as an error or infinity, correct? In the same way, another numbers if we took, two 8 digit, another set of numbers if we took, if we multiply them, again we are getting error or something infinity, okay? It doesn't means that answers of both the calculations, both that multiplications are same, okay? So here we are getting the same value, even though constituents are the different one, okay? Now anisotropy, isotropy, this is the first point of differentiation I told. Now the second one, that is crystalline solids, they shows cleavage property, and amorphous solids, they do not show the cleavage property. Now what is the meaning of cleavage property? Let's see. Here I will write cleavage property, okay, and they do not show the cleavage property. Cleavage property means when we cut the crystalline solid with the sharp edged tool, we are getting the smooth and plane surfaces. So ability to form a smooth plane surfaces when get cut with the sharp edged tool is known as the cleavage property. And opposite to this, if the amorphous solid, if we cut with the sharp edged tool, we are not going to get the smooth plane surfaces, okay? So that is the it means it doesn't show the cleavage property. For example, thermocol, if we cut the thermocol with the sharp edged knife or that hexa blade, so some thermocol balls 10%, some may get cut up to the 20, 30, 70, 90% or varying proportion. So whatever the surface of that thermocol, okay student, we are talking about the microscopically, just I am giving the macroscopic example, but microscopically we have to think, okay? So when these are get cutted, so there will not be a plain smooth surface, that is about the amorphous solids, okay? Plastic, rubber, thermocol, glass, wood, furniture, these are the examples of the amorphous solids. Further we will discuss. Now the next point of differentiation, A, C we saw. Now it starts with the H. What is the H? The heat of fusion value, delta H fusion. And here heat of fusion value is characteristic, and here the delta H value means heat of fusion value is not a characteristic one, it is not fixed one, okay? Characteristic fixed value of the heat of fusion is there. It means what? Suppose if we took 1 mole of a crystalline solid, and 1 mole of a crystalline solid, if we want to fuse it, if we want to melt it, we should give a certain specific amount of energy required to bring fusion of 1 mole of a crystalline solid, that is the heat of fusion, okay? In thermodynamics some more concept may get added, but in brief let me tell you. Now here that suppose if I give the 1 mole of the sodium chloride to the one student, for the another student I also give the 1 mole of a pure sodium chloride to the both the students if it is given. Now amount of energy required to melt that 1 mole of a sodium chloride to both the students, that amount of energy is the fixed one, okay? For the crystalline solid we require the exact fixed characteristic amount of the energy. It's not about the amorphous solid, okay? Amorphous solid, they may require the different amount of energy. The reason is hidden here, okay? Say for example, this is the amorphous solid, and in case of the amorphous solid, okay, the bond length, bond distance, bond angle, it is not fixed one. Okay, suppose 1 mole of whatever the bonds are present in 1 mole of the amorphous solid, so same number of bonds, same the bond distance, bond length, bond energy, these bond parameters are not identical. Okay, suppose if we took the another 1 mole of the that amorphous solid. Okay, so that's why heat of fusion is not characteristic one. Okay, it means what, sometimes we require less energy, sometimes we require more energy to bring its melting. Okay, now next one is that after heat of fusion, melting point. Melting points are fixed, characteristic and sharp one, and here there is no any fixed characteristic and sharp melting point. Easy to understand. For example, if we took sodium chloride, pure sodium chloride will have the melting point of 801 degrees Celsius, sharp characteristic melting point. Okay, iron 1535 degrees Celsius, so sharp characteristic melting point these solids have. But here, can you tell me glass, if we took plastic, okay, if it is homogeneous, that's the different part, but these solids, they are not having the sharp characteristic melting point. Reason is same. Say for example, this marker, this point of marker, if I take out, okay, and if I try to take its melting point, here this part if I took and if I try to take its melting point, so there possibility is that it is a different one. Okay, you may say it's a homogeneous, it is little same, but what I want to say, the constituents present here in this part and the constituents present in this part, the bond length, bond angle, bond distance, these are not identical. Okay, these are not a fixed one. So that's why amorphous solids, they are not having the characteristic melting and melting points. Okay, then next one, that is these are also known as the true solids. Okay, and these are also known as the ideal solids. I am talking about the crystalline solids. For amorphous solids, these are the pseudo solids. Okay, pseudo solids means what, appears to be a solid but they are not exactly solids. Okay, and some other names also I told earlier. Crystalline solids are also called as non-amorphous, ideal or true. Amorphous solids are called as pseudo solids, or non-crystalline solids, they are also known as the supercooled liquids. Okay, supercooled liquids. See, especially for the glass, the word used is a supercooled liquid. That suppose the glass is window glass is fitted, okay, and the construction, that glass is made, say for example 100 years back. What is noticed, the lower region of the glass is thick, okay, little thick, and upper region of the glass is thin one. Why it is so? So slowly, steadily, because of the gravitational force, these constituents in the upper region, they are reaching to they are going towards the downward direction very slowly. Okay, so these things are also noticed. Now next one, sixth point of differentiation is O. O stands for the order. Okay, here we have to take the meaning as order, long range order. Long range order. What it means? Suppose here there is a certain repeating pattern of the crystalline solid. Here another repeating pattern, here another repeating pattern, and this repeating pattern is get repeated again and again, three-dimensionally. So that we call it as a crystalline solid. Long range order. Okay, now something is placed in order. Okay, we say in a proper manner the things are get placed. So that long range order means that repeating pattern is get repeated again and again. Okay, here I am showing 3, 4, 5, 6 times, but practically some lakhs, some million times the repeating pattern is there in a crystalline solid. Okay, here there are the two things, either there is a short range order or no order. What it means, say for example this is the repeating pattern, 2-3 times it is repeated, but again it is not going to repeat. Okay, so repeating pattern is there, but not regular repeating pattern. Okay, so either short range order or there is a no repeating pattern. Say for example here no repeating pattern is there. Okay, so now next one is Okay, I told here that 7 part is also repeating pattern. Yes, specific repeating pattern is there. Okay, you are seeing, just I gave some example, and here there is a generally there is a no repeating pattern. Okay, and the last point is of the examples, crystalline solids examples. Okay, I'll try to tell the types of crystalline solid in next lecture. That is molecular solid, metallic solid, ionic solid, and covalent solid. Okay, that discussion will be there. But here crystalline solid examples are ice, okay, molecular solid, covalent solid example phosphorus, sulphur in solid state. These are the examples of the crystalline solid. Common salt, NaCl, NaBr, KNO3, KCl, all these are the examples of crystalline solids. Metals, iron, copper, zinc, aluminium, okay, alloys, these are the examples of the crystalline solids. Amorphous solids examples are which one? Plastic, rubber, thermocol, okay, glass, soil, wood, okay, all these are the examples of the amorphous solids. Okay, so the hint is what? ACHMTORE, anisotropic, cleavage, heat of fusion, melting point, order, repeating pattern, and examples. Okay, all these things are based on the figure. Okay, thank you.